Good morning, everybody. This is a brief introduction to the subtractive process called milling. Now, I have a very loose scale, which is not very well defined because machining is too broad a field to be well defined. And in it, I'm classing the three primary subtractive processes as turning, milling, and drilling. Subtractive means start from a large block of material and remove pieces, leaving the actual final design that you want at the end. Now, turning is where you have the tool fixed and you spin the stock against it. Milling is where you have the block kind of fixed and you move a tool into the block. Now, admittedly, in the video, I'm showing you a 5-axis milling process where the block is in motion relative to the tool. But that's very different from, say, the spinning and turning. But effectively, milling is where you're driving a rotating cutter into a piece of stock. And then also there's drilling, which is punching round holes in things, which will be described in another video. So let's try and talk about the definition of a mill. Milling is really hard. Turning was a lot easier. Turning, you had a machine called a lathe which did turning. In the case of milling, the machine's called a mill. A mill has been used for hundreds of years to describe thousands of different technologies. But the one that we're interested in is cutting or shaping metal with a rotating tool advanced into a workpiece. In other words, the work is somewhat stationary and the tool is advanced into the work. And you can see in this little video here the cutter progressing its way into making a slot and throwing the chips of metal it's cutting away out behind it. If we look at the history of milling, it came later than the lathe. David Gingery made a series of 7 books on building your own metal shop from scrap, starts with casting, and the first machine he makes is a metal cutting lathe. Well, and then a metal shaper, and then you can see the milling machine is actually machine number 4. Now, the reason is milling machines are quite complicated. They are also not as fundamental as a lathe, but on the other hand, their sheer power and flexibility makes them incredibly desirable. So the history is difficult because, again, with machine tools, thousands of people were working on them in their own way and constantly improving the equipment they had. But loosely speaking, the consensus is that people were putting a rotary file bit into a lathe chuck and spinning it and bringing the workpiece in contact with that to do filing and material removal that way. And it seems that milling machines kind of grew out of the desire to basically move the tool into the block in a controlled, repeatable way. Our most obvious milling machines began appearing in the 1810s, producing things like gears for clocks and gears for other machines and firearms and armories. But fundamentally, the milling machine is quite a complex machine which excels at flexibility and repeatability, and it is a very powerful and nice to have machine in any shop or manufacturing process. So let's look at the anatomy of a milling machine. Now, this is a classic Bridgeport Series 1, one of the most famous manual milling machines in the world. But don't be fooled by a more modern CNC computer-controlled one, because effectively, they're this machine in a box. If we took away the outer shell, you basically have something which looks very much like this and has the same kind of innovations. There are a couple of what I would call key differences, but realistically, the same idea applies. So the milling machine, the desirable properties that you want in a milling machine are you want the milling machine to be as rigid as possible. Okay, we're going to be driving a tool into something and expecting to remove pieces of the thing. If we drive a tool into something and the machine itself flexes, twists, or distorts, then we're not going to get the result we want in the actual metal itself. You know, we're using this machine to imprint our will into a raw block of material. If the machine is weak, then our will isn't going to fully be expressible by the system. So rigidity is hugely important. Then we need a powerful torquey spindle to twist the cutter through the material that we're doing. But spindle torque is directly connected to rigidity. If your machine isn't very rigid, you can't have a very torquey spindle, otherwise you're going to twist the machine more as it bites into something, and then the machine body can't support the power of the actual spindle. And kind of vice versa a bit. If you have a very rigid machine with a very feeble spindle that can't twist the tool very well in difficult circumstances, then you're not taking advantage of your rigidity properly. And lastly, one of the other things that is not in this diagram is power drive on the axes. And manual mills absolutely come with power drives, and they have for centuries as well. But basically, the ability to move material under the cutter or through the cutter at a consistent rate is hugely important. So now we've established what our desirable properties are, let's look at this Bridgeport Series 1. Now, the Series 2 was its big brother, but the Bridgeport Series 1 was struck a perfect balance of kind of size and ability, such that it became, well, as hard to find as a computer GPU is these days. The Bridgeport mill was the GPU of its day, totally sold out for years. You had to get on a waiting list. So they started with a cast rigid vibration dampening body, cast in grey iron. It's incredibly stable over time. It's incredibly good at down vibrations created by the cutting process, and it's a very heavy body, giving a lot of structure and rigidity to the whole system. And then on top of the body, you can see there's a ram sticking out, which leads into the motor quill head assembly, which pushes the tool and holds the tool. The work itself is bolted to that shiny steel table that you see there, which is called the bed. And the bed sits upon a knee, which goes up and down, giving it the Z-axis. And the bed itself slides left and right and front to back, giving you the X and Y. There's also a Z-axis in the quill, where you would reach and use a handle to lower the spindle down as well. But you should really only be using that for drilling, because again, when you've got a block of steel bolted to the table and you're moving it sideways under the cutter, if you can avoid using the quill, that's great, because we mentioned you wanted rigidity, right? Well, the longer you stick out the quill and the longer your tool is, the more bendable it is. It's very much the same as if you have a stick and you wave it in the air and it whips backwards and forwards. Well, if you cut the stick short and whip it, it doesn't move as much. Exactly that mechanical principle underlies this idea that using the quill for drilling is great, using the knee for most of the other heavy Z moves is better. Usually a little bit of quill movement is perfectly acceptable. It's a kind of trade-off between convenience versus rigidity, which is what you want. So we've done the head, we've done the quill which holds the tool, we've done the bed, we've done the knee. Effectively, this is all kind of the package. It's rigid within itself, it's a kind of open C shape, and it is a very flexible machine. So why would you reach for a mill? Mills bring in one package this fantastically adaptable rigid system. The rigidity supports the repeatability, and using this fantastically adaptable system, you can make a really wide variety of operations leading to these wildly different parts with a high tolerance, high repeatability, quickly, because you're not constantly having to rebuild work holding on the table. And if we look at the parts, you can see they're all fairly rectangular. It is totally possible to do circular parts on a mill using an indexer, but basically it excels at producing accurate drill holes versus bodies versus structures. So your mill is your win for flexible, complex parts of all kinds. One thing to note about the paths, and we'll talk a lot more about this in mill operations, is you can see you've got sharp outer corners, but if you look at the inner corners of a part, you can see that they're rounded or the holes are circular, and that comes from the spinning cutter. It's very hard to impose a 90-degree turn on the corner on the inside of a cutting piece when you have a round cutter, round like my finger is round, going round here. You can't make a 90-degree corner here. On the other hand, on the outside of the piece, you absolutely can use a round cutter to cut a very sharp right angle just by moving it correctly. So, why is a mill great? It's a very rigid structure with a huge amount of operational flexibility to deliver these parts. Let's talk briefly about CNC mills. We had one doing 5-axis operations on the title slide that we have in the Bechtel Center. They are just like the manual machine, except they, generally speaking, have a metal box, making them somewhat safer, because the spindle and chips are contained, and they execute a computer program which drives the mill by electrical motors in a repeatable way. They allow themselves to be highly automated. This system here has a pallet loader, which is just going to operation now, where it's going to swap the 3 finished parts for 3 parts that aren't completed. Just notice the guy waving. Yes, we see you, guy, whoever you are. But fundamentally, they support a large amount of automation, and they repeatedly produce parts with very high tolerance in production environments. Manual mills are still pretty popular. Many shops and factories have one or two around for the odd jobs. As soon as you get into mass production of stuff, though, you're going to be using something like this. At the center, we have both. A last word on mills would be the coordinate system. We talked about coordinates in the lathe, where it basically only has 2 axes, while mills have 3 axes, and here they are. So X is the bed moving left to right, right being positive. Y is the bed moving away from you or towards you, with away from you being positive, and Z goes through the column. And the one thing that I always find terribly counterintuitive is positive Z is up and negative Z is down. And nearly always you're bringing the cutter down into your work. So it's kind of weird that for whatever reason, I always feel that the Z-axis should be the other way, but it isn't. So always remember, minus Z is down, positive Z is up. So all in all, a powerful package of, it's very flexible in what you can use it for, and it's a very rigid structure which can basically do a fantastic job of producing drill patterns and slots and holes and corners and pockets and facing a block, i.e. taking a raw piece of stock and making it a nice squaring it up. And if you put a rotating table onto the bed and bolt it down, you can even do a lot of lathe type operations of doing radii in corners. All without removing the workpiece from the bed, which is a colossal pain, which we'll talk about more in work holding. But work holding is one of the 2 main problems in machining. You have holding the tool and holding the work. Thank you very much, guys. Have a good one. Goodbye.